thought we'll wait couple of minutes for others to join. And then I remembered that I had this as the last slide in my presentation yesterday, but I didn't show because I stopped since our time was over. So if any of you are interested or if any of your groups are interested, I think you should consider attending this course. So I will cover parts of it today, but this will be a full day course that I will do along with Dr. Nicholas Curry, who did his PhD with us, and then he joined a company in Austria called Treibacher, which makes suspensions for thermal spray. Now he is partly a consultant and partly with a company called MedTech, which makes plasma spray systems. So he has very good experience, and we thought we will do this course together. This date is very special because this happens to be my wedding anniversary. But no, jokes apart, this is one day before a National Thermal Spray Conference, which is being held in Bhubaneswar on 21st and 22nd. So it's not as though you must travel only for this course. There's a National Thermal Spray Conference that happens on 21st and 22nd, right? So if you look up the Indian Thermal Spray Association website, you will see this. Yeah. Who? This conference is at CSIR IMMT in Bhubaneswar. There is another conference on additive at IIT Bombay. That's next month. But this one is in February. So, I think now maybe we should start. Yeah. So based on what I heard from you guys yesterday a little bit, and as I promised, I thought today I will dive into one of the surface engineering technologies, not talk about everything. I gave a general overview yesterday, which hopefully conveyed to you how powerful surface engineering can be, what different kinds of coatings you can deposit, from thin to very thick, from metal to ceramic to intermetallic, everything, right? And then I thought I will today pick thermal spraying as an example. And as you heard, each of those techniques that we spoke about yesterday, whether it's PVD, electrodeposition, even hardening, all of them have many variants within that family, right? So I'm going to take as an example thermal spray and talk about what is new in thermal spray, because I think that is one of the objectives of this course as well, to talk a little bit about fundamentals, to also give you some indication of what the research areas are, which are new, right? So let's start with very fundamentals first, right? So that I don't lose any of you, right? And once you understand what thermal spraying is, then you'll be able to better appreciate what comes next during this 1.5 hours, right? So let's begin by discussing what is thermal spray. Again, let's go to the definition. So as per definition, thermal spray is a process in which surfacing materials are heated to the plastic or molten state inside or outside of the spraying gun or torch, and then propelled onto a prepared surface. Prepared surface is actually surface of the component that you want to coat, right? And the substrate remains cold. It's the material that you are coating which either gets to the molten state or at least to a plastic state, yeah, by the time it deposits, yeah. And to obtain a certain specific property on the surface, you will change this material, of course, right? So if you want insulation, you will use the ceramic. If you want corrosion protection, you can use anything from aluminum to things that are far more complicated. Aluminum to nickel aluminum to nicrol to nicroly, right? Where Y is yttrium. Yeah. So you can make it as complicated as you want, depending upon what kind of performance you desire, right? So, so the specific property that you get from the coating is dependent on the material that you use. There are also various post treatments, just like in AM, you can do some post treatment to a coating. You can do some thermal post treatment to densify. Sometimes you can do mechanical post treatment if you want the coating to be mirror finished. Yeah, you can do that. Sometimes if you don't like any porosity at all, you can do sealing after the coating is over, right? So many possibilities are there, and we will talk about some of those as we go along, if necessary. Yeah. When it started, thermal spray, it started by accident. There was this gentleman called Max Schupp who was playing around in his lab, and suddenly while he was doing something on his desk, he found metal droplets going and depositing on the wall, yeah, because of some explosive or high velocity gas that he was using. So that was the beginning of the idea of thermal spray. At that time, Max Schupp called it metallization. Even today, some people refer to it as metallization when they are talking about aluminum, zinc, or aluminum arc spray and things like that, right? So it used even lower melting materials like tin and lead, right, to deposit. Now, of course, we have gone way beyond that. So metallization at that time involved atomizing this molten metal and propelling it at high velocity to impact on a surface and form a coating, right? After that, it came to feeding wires or using oxyacetylene torches, etc. But just to let you know that thermal spraying, as per what began as metallization, is almost 100 plus years old now. And because of that history, it has evolved in a big way, right? So this is a very busy slide. I don't want you to read anything. What I want to tell you is, although it started at around 1900 by Max Schupp, today all these boxes are some variations of a thermal spray gun, correct, that is available. So things have changed quite a bit. Yeah, somewhere along the way there was oxyacetylene, then there was plasma, then there was high velocity oxy fuel, then air fuel, then cold spray. So all this is shown in this graph. So let's not get into that for the time being, right? Just be aware that many such things exist which we call process variants within the thermal spray family, right? How versatile is this process? So I told you it's 100 years old. There are many techniques available. How about materials? If you take a catalog now from a supplier that of only thermal spray powder, yeah, again, you can't read, but there is a reason. I don't want you to read. Yeah, I only, if I can zoom, I want you to only read this, right? This catalog runs into 43 pages from one supplier. So there are 43 pages of list of powders that you can thermal spray. So you can imagine how versatile this field is. All of these powders written on these 43 pages can be thermally sprayed. Yeah, you see some categories here. Although this is a lousy slide, you can see M. Crawley alloys, you can see metals, alloys, and other composites. You can see carbides. Yeah, you can see many oxide ceramics. All of these can be sprayed, right? So we spoke about how many different process variants are available, and here I am trying to tell you that there is a very large portfolio of feedstock materials. So between them, you can create many kinds of fun coatings in a manner which is completely traditional, right? So let's see how thermal spraying is conventionally practiced. Traditionally, how do people do thermal spray? And then starting with those traditional practices, how crazy guys like us have distorted thermal spray to do something totally different, right? But let's first, to appreciate what we are doing, you must understand what is conventional, right? So the conventional way, one more time, to show it as a cartoon. So you inject the material that you want to coat in a high temperature, high velocity zone. What is the intention? The intention is that this material that you introduce should be molten, yeah, and then the molten droplet should be accelerated, yeah, and accelerated to then go and hit a surface. What happens when a droplet goes and hits a surface? What do you think happens? If there's a molten droplet that goes and hits a surface at high velocity, what do you think happens? Metal pushes out. Any better definition? Molten droplet hitting a substrate at high velocity. What happens? Spreads. Okay. Huh? It splats. Yeah, that is the correct word. Right? A molten droplet comes, hits a surface at high velocity. Yeah, it forms a pancake almost. Right? It splats. Not hard to believe, right? You have a molten droplet comes at high velocity, that droplet spreads. So it forms what is called a splat. Now these splats, if you are moving the gun, for example, these splats can be overlapped. So you can cover large area, as large area as you want, as large area as your holding mechanism in your spray booth allows you to vary, right? If you have a robo gun on a robo, it can do whatever is the reach of the robo, correct? So you can cover large areas by overlapping these splats. How do you build thickness? You stack up these splats on top of one another. Yeah, you build thickness. Very simple. This is thermal spray in 30 seconds. You melt material, accelerate, splat to form a dish-shaped splat, overlap splats to cover large area, stack up splats to build thickness. Over, correct? Now you are all thermal spray experts. So let's talk about a couple of things. Why do you want the particle to fully melt? What happens if it does not fully melt? Yeah, suppose it's not a nice droplet. It has a molten skin, but the core is still solid. Imagine. It can happen, right? That your particle is not fully molten. It's partially molten. Then what happens? Okay. What happens? Yeah? It doesn't form a pancake very nicely, right? And it's coming at high velocity, so the middle part which is not molten, it can bounce back, right? Because it's not spreading. Then what happens if it bounces back? That becomes a reason to form porosity in the coating, right? One. And why do you want it at high velocity? Because these are all mechanically anchored coatings, yeah? So before you do this coating, you roughen the substrate by grid blasting, right? So why do you want high velocity? So that these splats, because of the roughness, can stick properly, correct? If it's a very smooth surface, it doesn't stick. If it is not fully molten also, it doesn't stick, correct? So that is the ambition then for a good thermal spray practitioner. Fully molten to avoid porosity, high velocity to get good adhesion. Yeah? That is the mantra all the time. So this is how thermal spray has been practiced for several years. This material, by the way, you can feed it in many different ways. You can feed it as a wire if you want. in certain spray systems. In very rare cases, you can feed it as a rod, but most popularly, you feed it as a powder, correct? Easy to understand, yeah? So when you talk about different variants in the thermal spray family, the real difference comes here. How is this high velocity, high temperature zone created? What is the temperature in that zone? What is the gas velocity in that zone, correct? So all these different plasma, detonation, HVOF, HVAF, cold spray, they differ here. Yeah, this part is the same, this part is almost the same, right? The real difference is coming here, okay? That's important to understand. So a closer look. These particles strike the substrate, hopefully in molten form, right? So if you do it right, these molten droplets will form a splat, yeah, and these splats will stack up to form thickness, yeah, very simple, looks like, yeah. So in a way, this splat, I like to call it, splat is a building block for a coating, right? Just like a brick here, right? You can put bricks side by side. Similarly, you can put slats side by side with little overlapping. You can put slats on top of one another. This is the simplest way to visualize a coating. Is everyone with me? Nobody is lost? Nobody is confused? Because if you don't understand this, then next 1.5 hours is a waste. Yeah? So this is important to understand. Yeah? Okay. Good. So same as what we spoke yesterday, if I pick the right material, yeah, I can achieve any function from thermal spray, right? I can get corrosion resistance. In the simplest case, people spray bridges now in the US with thermal spray. Only do aluminum or aluminum zinc, right? So you can get corrosion resistance. You can get very aggressive corrosion resistance in a land-based gas turbine where you won't use aluminum or zinc, you'll use something far more complicated, correct? But you can get corrosion resistance. We already spoke about zirconia yesterday, I gave that example. So if you want a thermal barrier or insulation, you can do that. You can get electrical conductivity. Copper on aluminum is a very popular application for cold spray, for instance, right? We spoke about abradable coatings. What did we call it yesterday? What was this called? Clearance control coatings, yeah, or sacrificial, yeah. So it was that category. You can get other textured surfaces. We also spoke about implants and prosthetic joints, right? So by using the right powder, you can get all these functions by thermal spraying, and that's what makes it very, very useful, yeah. So advantages, these are clear to see. I've already spoken about that. Many materials, list running into tens of pages, can be sprayed. There is no great heat input to the substrate unless you do this process in a very bad way. Your substrate doesn't get heated. Why? Because you have one droplet coming and immediately cooling. It is impacting a large substrate. The substrate itself serves as a heat sink. Yeah, so there is no reason for any heat up on the substrate. Yeah, if the part is very small, let's say I'm coating this part. Many times you have to do things like that, and then I'm not coating. I'm not doing that, right? Otherwise, if I do like that, then if a particle hits here, by the time I go there, this has already cooled, right? Then I come back. But imagine this is what I'm coating, yeah? Then it's almost always on the part, right? Doesn't have time to cool sometimes, right? Then there is a chance that it will get heated up, and then in such cases, you must make some mechanism for cooling, correct? Which is also possible. So all this can be done. Many times with certain types of guns, you can work on site. You can just put it on a truck, go there, repair and come back, or coat and come back. Yeah. So that is possible, and most of the systems today are automated. Automated to the extent that if a human being is inside the enclosure, the gun doesn't even operate. Yeah, you can't even start it. Yeah, so there is that level of automation now for reasons of safety, etc. Yeah, so very sophisticated now. What are the problems? Yeah, we spoke about this little bit. It's a line of sight technique. What does line of sight mean? BTech. Correct. Yeah. Whatever the gun can see, it can quote. Yeah. So for example, if I am doing this, I can't quote here, obviously, right? Are there quoting methods that can quote here? Not thermal spray. Are there other methods that can quote here? Yeah. Many can quote, right? Electrodeposition. I just dip it. Yeah. Or PVD, CVD. There are several which can quote, but thermal spray can't do that, right? Because it's line of sight. You need surface preparation. I spoke about grid blasting. Yeah, you have to roughen the surface. What if I am coating something like this and I want a coating only on this side? Yeah, I cannot tolerate any coating here. Yeah, it's a big problem for me if any material deposits here. What do? You have to do masking. Yeah, you have to do masking. Even that has a long history. Earlier people used to do simple tape masking, right? But as a race, human beings are very greedy, right? You want everything better, right? So to get more and more addition strength, we have, I will come to that later, we have come up with thermal spray techniques which are extremely high velocity, more than 1,000 meters per second, right? And you are spraying for better tribology where you are spraying very hard materials, right? So imagine very hard materials heating at 1,000 meters per second, yeah? Then tape masking doesn't work anymore. What used to work earlier for normal different kinds of coatings suddenly doesn't work because you have come up with harder materials, you have come up with processes that provide much higher velocity, and then that masking doesn't work. So in that case, you have to use metal masking, right? So masking also becomes a big step when you are using techniques like that. Yeah, all these are not really shortcoming, but yeah, you need to know that some of these can be loud. So if you, for example, talk about detonation spray, it's 80 decibels, 80 to 100 decibels. It's like standing underneath an aircraft, yeah, engine which is running. It's that loud, and it's also a sensitive process, more sensitive as you start using new feedstock. Yeah, we will talk about that later. Is everyone clear so far? Any confusion? Yeah, does anyone have questions about why you grid blast, why you mask, stuff like that? No? Yeah, very clear? All right. From yesterday, I've been talking about microstructure and the importance of microstructure in AM, in coatings, etc. Let's look at how a thermal spray microstructure looks like, right? It looks lousy, to be honest. It looks terrible. If you look at thermal spray, inherently it's a defect-prone microstructure. It's prone to all sorts of defects. Let's see what kinds of defects exist. Yeah, porosity. No matter what you do, some porosity will be there. Correct? Arising as these flats stack up. Some powders, you always have a particle size range. Some particles melt, or many melt, and some do not. Right? So there are reasons why you get porosity. Sometimes you get oxides. When you are spraying oxide materials, that's not a problem. But when you are spraying metallic materials, because of the high heat input, some oxidation can take place. And your application then decides whether a certain level of oxide content in the coating is acceptable or not acceptable. Right? But oxide content is another important characteristic. People at least the industrial users always question about addition. So if you run a thermal spray job shop, a user will come and ask you, what is the addition strength, or also called bond strength? What is the bond strength of the coating? Why they ask that, even they don't know most of the time, but they ask, what is the bond strength? So you should know how to calculate bond strength or determine bond strength. And just like which AM process has most residual stress? Go back to yesterday or day before yesterday. Huh? Wire arc has residual stress. SLM has residual stress. So similarly, thermal spray coatings also have residual stress, right? So some of these are very typical characteristics of a sprayed microstructure. Remember, we are right now talking about conventional thermal spray. Some microstructures I show here. These are plasma sprayed zirconia thermal barrier coating. Fair bit of porosity, but porosity is good in a thermal barrier coating. Why is it good? There are a couple of reasons why it is good. I would like to hear at least one. Why is porosity good or okay in a thermal barrier coating? Reduce the heat? Yeah, it kind of reduces the thermal conductivity of the coating, which is what you want if you are putting on an insulating coating. What's the other reason? Imagine a thermal barrier coating which was fully dense, no porosity, no nothing. Would it survive? No, it will not survive because of thermal stresses, right? There is no way to accommodate thermal stresses if it's fully dense, correct? That it will bond. Here the bonding will be good, but if there is no porosity, yeah, there is no way to accommodate thermal stresses. Imagine that you are a coating in an aircraft, and the aircraft is taking off and landing. So what does it do? It's basically heating up and cooling, and that induces thermal stresses. How will the coating accommodate stresses if there is no porosity, right? Then it will immediately fail here because of the stresses. So we asked yesterday if porosity is good or bad, and we decided it depends. Yeah, so it's part of that, correct? So it depends. In some cases, this is all right. In other cases, if I'm looking at a wear coating, even this kind of porosity is not all right, correct? All right. So let's come back to this, the same schematic in a slightly different way. Yeah, material feedstock, spray process. I said this is where the difference lies. Yeah, how is the high temperature, high velocity zone created? There are typically three ways in which you create. Sometimes it can be electrical. Electrical meaning you just strike an arc. Yeah, you immediately create a high temperature zone. Yeah, if you have two wires striking an arc, then you create a high temperature zone, and those wires themselves serve as material. Yeah, and these if you have a carrier gas, they take away droplets from that and form a coating. In some cases it is by combustion, this high temperature, high velocity zone, that is most common. Yeah, the simplest form is oxyacetylene flame, but yeah, now you use, depending upon which part of the world you are in, you can use propane, propylene, that kind of stuff. Yeah. In yet other cases there is no flame at all, it is just kinetic energy. We will talk about that a little bit. But what I actually wanted to talk about here is, what is critical is gas temperature and gas velocity in this region. What is also critical is, from this point on, let's assume that we are using powder, right? What is also important is powder particle size, right? Because both of these together will decide how fast the particle gets heated up, whether it melts or it doesn't melt. It will also decide how quickly the particle accelerates, and therefore at what velocity it will go and hit the surface. Is that clear? Yeah. So So these two, as you can imagine, are the most important governing factors in deciding what happens to the particle before it goes and hits the substrate, right? So when you're optimizing parameters, you're usually playing around with this or with this, correct? Yeah. Yeah. So we quickly spoke about electric methods, combustion methods, and kinetic. If you break that down further, I spoke about wire arc. The other is plasma spray. Yeah. What is plasma? Can anyone define a plasma for me? Anybody? I'll give you a hint. It's also called the fourth state of matter. Yeah. What are the three states of matter? That you know. First, let's start with that. Solid, liquid, gas. Correct. 100 out of 100. Yeah. Fourth state of matter. Partially ionized gas. That's apparently the fourth state of matter. So you are working with an equipment that ionizes gas and utilizes all the energy that's available there, thermal energy, to melt and accelerate the powder. The other technique, as I was talking about, is combustion. The oldest is oxyacetylene combustion. We spoke about that a little bit yesterday. Yeah, but now there are many more advancements in that. You have new gun designs which still rely on combustion but enable extremely high velocity in the gun. So high that you get shock diamonds. If you look at the flame, you see shock diamonds. When do you see shock diamonds in a flame? Anyone know? When do you see shock diamonds in a flame? Anybody? When the velocity is supersonic. Yeah, that's when you begin to see, even with your naked eye, you see shock diamonds, correct? So you now have spray systems where you rely on combustion, use oxygen and propylene, for example, but enable extremely high velocity that gives you shock diamonds, right? Now, I spoke about greed. We are greedy. Even that is not okay for us. We want still higher velocity. So people started using air instead of oxygen. Yeah. So if you want to do full combustion, you have fuel, you have oxygen, it combusts, right? What do you think is the advantage of using air? What happens if you use air instead of oxygen? Just think. What happens if you use air instead of oxygen? Why would people want to use air? No other type of gases, nothing. You still need oxygen for combustion. Why do you use air? Yeah? Imagine that you needed X liters of oxygen for full combustion of a fuel. Yeah? X liters of oxygen. How many liters of air would you need? Roughly. How much? If I needed X liters of oxygen for full combustion, for the same combustion, how many liters of air will you need? If it is X, you tell me 0.2X or 2X or 3X. How many X will you need? You'll need almost 5X, right? Because 20% is oxygen, 80% is nitrogen in air, correct? So you'll need 5X air, correct, for full combustion. Now if you provide 5X air, what will it do? It will further give acceleration. You are introducing even more gas, right? So your velocities become higher and your flame becomes cooler, right? Because there is so much non-combustible nitrogen that is available, yeah? So you're getting much higher velocity but much cooler flame, correct? So that is why our greed has taken us to HVAF and you get beautiful coatings because of that. We'll talk about that a little bit. And the third is something called cold gas dynamic spray. To me, all of these are additive manufacturing, to be honest, right? But people now consider this as a big part of additive manufacturing, yeah, for repair, etc. Cold spray or cold gas dynamic spray, depending upon who you are talking to. Uh, the, uh, the terminology is little different, but they are the same, cold spray or cold gas dynamic spray. So how do they compare? As I said, the most important thing for you to consider is temperature and velocity. So let's map all these processes that I showed on this slide on this map, right? Let's plot temperature versus velocity, right? So you have plasma, which is the big daddy. People thought all thermal spray problems were over when plasma spray first came into being because of this kind of temperature. Imagine almost 15,000 degrees is the temperature that you get, right? So people thought all problems over. You can melt anything that you introduce under the sun as long as you do not sublime. It shouldn't be a material which sublimes. All of you know what sublimation is? Silent direct vapor. Yeah, as long as that doesn't happen, you can melt anything in a plasma spray. Yeah, so this gives you the highest temperature, and we spoke about cold spray. It gives you lowest temperature because there is no thermal energy, there is only kinetic energy, correct? So this is the map. So if you want to buy a spray system, it's important for you to think about this map. What am I going to spray? What temperature does it need? What is the application? So this map is very useful for you to understand what is going on, correct? Yeah, we'll come back to this if necessary, but these are what are most popular today. If you go and look at thermal spray literature or thermal spray market, among the oldest simple flame spray, you have oxygen, you have acetylene, you use a normal lighter, it lights a flame. Your powder is in this canister, you feed the powder into the flame and you're all set, right? The flame will melt this powder and then everything that I said just now will happen. Then some people started into the same flame feeding wire. So you have a wire spool here, feed wire, wire comes out here. Same thing happens otherwise, just like with the powder. Then people started using arc. So 2-wire arc, yeah, strike an arc, have a carrier gas. The wires melt at this tip and the carrier gas carries the droplet to form a coating. Yeah. So now you understand the mechanism, right? What you are trying to do, you understand, right? And then plasma, of course, detonation. Again, relies on the principle of combustion, but you have a high pressure chamber which is pulsed. So it's like if you go to ARCI sometime, it is like shooting, tuck, 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 you will hear that sound, yeah? And that is determined by what is the frequency at which you allow it to pulse, right? It can go up to 8 hertz frequency, which means it will pop 8 times a second, right? And each time there is a detonation, you will inject powder and that will get melted and accelerated, right? HVOF, say almost similar principle as this, but this gun is modified so that it can deliver very high velocity, yeah, of both fuel and oxygen, and therefore you get very high velocity. This is what I told you. This is a picture from my lab. Yeah, here instead of oxygen you are using air now for the reasons that I just mentioned. Much higher velocity, cooler flame, right? And then this is cold spray. This is a picture from ARCI, but you have many variants of cold spray. Let's talk about cold spray a little bit, right? I told you there is no thermal energy, yeah, only kinetic energy. So what does it do? If you are using kinetic energy and you think back about what I said, how coating forms, yeah, a droplet or a particle comes, hits the substrate, spreads out, forms a splat, forms a coating. So if it is cold spray, no thermal energy, how does a coating form? Anyone? Anybody? How does a coating form in case of cold spray? Gravity. So in the definition you said particles which are plastic or molten, right? In this case the coating forms by plastic deformation, not melting. How many of you have heard of plastic deformation in the first place? Yeah, some of you have heard plastic deformation. So therefore automatically, why are you adding permanent unnecessarily? Yeah, just say yeah, plastic deformation. Okay. So what does it mean? If you have some ceramic, can you deposit by cold spray? You can deposit by cold spray because it won't plastically deform. So that becomes an additional limitation of this process, that you can only deposit materials which can plastically deform, right? Like most of the metals do, right? Aluminum can plastically deform. Zinc, all these things can plastically deform. Ceramics don't, right? So that automatically imposes a limit on what you can spray and what you cannot spray, all right? So that's important to understand. So let's talk a little bit about what is new in thermal spray. Let's talk about three things. Let's shortly discuss three things. What's new in equipment for thermal spray? What are the advances in feedstock? Maybe I'll spend most of my time talking about this, and also with processing, right? Moving forward. But all of you are clear about what is present day thermal spray, right? Conventional. Now you're clear, right? Let's talk about equipment and feedstock development, because that really sets the tone or lays the foundation for what comes new or next in thermal spray, all right? Let's look at some advances in thermal spray equipment. One of the recent things is called a new gun from Saint-Gobain, which allows use of a flexi-cord, right? Just as we spoke a little bit about limitations of cold spray, where we said only materials that can plastically deform can be coated. What is the disadvantage of arc spray, wire arc? What do you think? Yeah, two wires forming an arc, and then that material being carried away by a carrier gas. What's the limitation of that process? That your feedstock has to be conducting. It should strike an arc, correct? If it doesn't strike an arc, that process doesn't work, correct? So in flexi-cord now, yeah, people do many fun things. The exterior is conducting, and it could have ceramic packed inside, right? So it's a flexible cord. There is a way to strike an arc, but there are all sorts of materials inside the cord, right? So that's a big advantage. It's also useful that you can inject that flexi cord through the center of the gun, right? And today you get these kind of flexi cords or wires in many different diameters, in many different chemistries, just like powder. Otherwise, the ability of a material to be drawn into a wire was a constraint when you wanted to do wire arc spraying. So you're removing that constraint in a sense. Yeah. This is a high velocity air fuel system from my lab. Looks very nice, doesn't it? Right? Very stable flame. Yeah. We use this mostly to spray tungsten carbide, and this will give you an idea of how high the productivity is. Beautiful flame. We put on almost 10 to 20 microns per pass. Every time that goes around, you build 20 microns, so it's pretty quick. Yeah, in about 10 rotations, you build 200 microns on whatever part. So that's a big advancement. I spoke about it a little bit, but very quickly, let's compare HVAF, which is new, with high velocity oxy-fuel, which is old, right? And see what are the differences. The main difference is that you use air instead of oxygen, right? Compressed air instead of oxygen. We also spoke about what that leads to. It leads to much higher gas velocity because you are using 5 times as much gas as you would if you used oxygen, and therefore it lowers the flame. Why is this interesting, right? Why are both of these interesting? Lowering the flame means that there is no thermal damage to feedstock. We spoke about what different defects can be present in a thermally sprayed coating. One of them was oxidation. Yeah, you could say that in some cases there is also elemental depletion. None of that happens if the flame is a little bit colder, right? And second, of course, is higher velocity where you get extremely good addition. So today, if we do an addition test, there is, by the way, an ASTM standard C633-79. What do? You almost exactly this size. You coat a 1-inch button, right? And then glue it to another 1-inch button, right? And try and pull it apart in a UTM, right? And the force at which you pull it apart is the bond strength or adhesion strength of the coating, right? That's how it's done. So when we do HVAF, we always get failure in the glue. We never get, because there's no glue hard enough to kind of overcome that bond strength. So we have come up with new ways of testing, like brazing or something like that, to be able to do that test. Yeah, so it gives you excellent adhesion, almost no porosity and things like that. We also have a handheld version of this gun available now, right? So that we can, we have actually taken this gun to a boiler, gone inside, sprayed it and come back, yeah? And many of the boilers in Sweden operate on waste material, so therefore they are prone to corrosion a lot, and therefore they need protection when they use that kind of starting material in their boilers, and this is a good way for us to go in there and protect those boiler tubes. Yeah. The other thing that is new in the thermal spray world is the availability of axial feed capable plasma spray torches. Historically, this has been the holy grail for thermal spray practitioners. You could never inject the material through the center, right? You always injected it radially outside in the plasma flame, right? Two things happened because of that. One is you could not utilize all the energy that was available in the plasma because it didn't come right from the center, yeah? So you wasted a lot of thermal energy that was available. The other is if you introduce it radially, the powder behaves in a very different way. It behaves crazy. If your powder particle size is fine, it just doesn't go in the center. It bounces off. Because at that temperature, what's the plasma temperature? I showed you. How high is the temperature? 15,000 degrees, right? So at that temperature, the gas is very viscous. The viscosity of the plasma plume is huge. Yeah. So if you have fine particles, they cannot penetrate the plume because of the viscosity. To overcome that, if you increase the carrier gas flow rate, some of the heavier particles just because of density go right through, right? So you then need a very precise window for the right kind of particles to go through the center, right? Instead of that, if you can inject it axially, like here, then everything works well. Your thermal energy is used up fully, your particles travel in a manner that you would want them to travel, and that leads directly to higher deposition efficiency, right? So this is also something which is very new in plasma spraying, yeah? I'm showing the same problem in a magnified sort of way, yeah? So there is segregation of powders that happens. You need higher carrier gas flow if these kind of particles need to come to the center, right? And then beyond a certain particle size, you cannot do anything. they just bounce off, right? So that's the problem with radial injection, which is then solved if you manage to feed it axially, right? Uh, that's not so important. Let's talk about feedstock. We spoke about equipment. Let's talk about feedstock. What is new feedstock available? Yeah. So today we can spray all this entire family of materials: metals and alloys, ceramics, cermets, even polymers. I showed you one picture about cookware, frying pans. People do that by thermal spray as well. Yeah. And we have now graduated to look at many new classes of materials. We already have few publications on all of these things: high entropy alloys, graphene, carbon nanotubes inside the coating. So these were not traditionally materials that one would thermal spray, but we are able to do all of these today in thermal spray, and that just expands this window of what you can do and what you cannot do, right? To give you a better example, we are a very small group, yeah, extremely small, and these are all the materials that we actually have sprayed in our lab. Just imagine, right? All sorts of nickel-based superalloys, 625, 718, CMSX4. All of these are mostly for repair applications, right? If you want to repair an existing superalloy component, we can spray all of these materials, right? A range of M-Crawleys, all of these are bond coats for TBCs, right? Some are pretty simple. We use these kind of things for instance, boiler applications that I mentioned, yeah? And these more complex bond coats we use for gas turbines, right? We have sprayed a range of cobalt-based alloys, titanium also again for repair. Look at oxides, we do all sorts of stuff. If time permits at the end, I'm going to talk a little bit about battery materials, right? Very complicated materials, but we are able to spray these as well, yeah? My dream at the moment is to combine solid lubricants with a wear-resistant material, and that's why we have been working on graphene, tungsten disulfide, also hexagonal boron nitride. We are also looking at hard materials such as diamond and cubic boron nitride. So this is a range of materials that is sprayed by a single group, yeah? I'm not putting this up to show off, but I'm putting this up to let you know that your imagination is the limit. If you use the right material and the right process, you can do almost anything, right? Powders, with AM, we were talking about, oh, you must use gas atomized powders. They should be perfectly spherical, otherwise you can't feed them, yeah? I've just picked out some powders that we use in our lab in thermal spray. All of these can be fed. All of these get fed nicely, and they form good coatings. So no problem. Yeah, you don't really need to have spherical powders, right? It can be angular, it can be agglomerated and sintered, it can be sintered and crushed, anything. Yeah, it works well as long as you know what is happening and what you want to achieve in the end, right? If you know, then you can get there. I want to talk, despite all these different feedstock that is available, I want to talk a little bit about some opportunities and compulsions that drive you towards looking at new feedstock. Because one of the things we wanted to deal with during valedictory function is new areas of research. So I want to cover some of that part here just now, right? So let's talk about opportunities for a new feedstock that synchronizes with new equipment that is now becoming available, yeah? Then these also make for very good research topics if some of you faculty are going to apply for grants, right? And then we began by talking about sustainability, right? There are some kind of materials which have been used by industry for many, many years, but now we are raising questions about use of those same materials, right? So you want to find appropriate replacements for those materials which are used currently in very large volumes, right? So you want to look at replacement for that. Yeah. So these are some of the new developments. One is availability of rods of different composition, not very new, but this synchronizes well with new equipment that allows rods to be fed. Yeah. We are very excited about this FlexiCord because just 2 weeks back on my way to India, Saint-Gobain, they launched something called cord plasma spray, and that's a result of all the work that we have done in our lab with their FlexiCords. So it's the first time that we have shown that even using a cord like this with zirconia, you can get columnar structure, right? So that's a big thing right now for us to be able to get columnar structure with a cord like this. Nobody's shown that before, right? So this is something that is happening because of the new axial feed plasma torch that is available, right? So you must exploit new equipment by coming up with new feedstock, and that combination can give you a lot of advantages. Let's talk about sustainability a little bit, right? Because that's the central theme of this course, right? If you look at tribology and wear coatings, and I'm happy if someone wants to argue with me about that, the only material that comes to mind is tungsten carbide. Yeah, for any thermal spray coating industrially used, what comes to mind is tungsten carbide. Chrome carbide comes a distant second. When do you think of chrome carbide? When you're thinking about higher temperature application, because tungsten carbide can be used only till about 500 degrees or something like that. So beyond that, you cannot use that, right? So if you are looking at higher temperature wear, you consider chrome carbide, otherwise not. Yeah. The first use of tungsten carbide was way back in 1942, right? Almost 80 years ago, people started using tungsten carbide. So not much has changed, yeah. And if I'm a researcher, I'm depressed to see that if I'm looking at wear coatings, nothing has changed for last 70, 80 years, right? It's not good. There should be something new happening, correct? Let's look at other problems with tungsten and cobalt, right? Both of them are fairly high on what is called the critical raw materials list in EU. We spoke a little bit about that. 50%, more than 50% of tungsten comes from China, and that's not nice, right? If you look at cobalt, it's even worse. Almost 70% of cobalt comes from a tiny African country called Congo, and this is bad situation to be in, correct? On top of that, cobalt is also, it has all sorts of health issues associated with that. So you don't like cobalt, you don't like tungsten either, but tungsten carbide cobalt is used in large tonnages by the industry today, yeah, to solve their problems of wear, right? So we in our group have been looking at, can we first of all eliminate or minimize cobalt? First question. Second, can we also replace both cobalt as well as tungsten carbide? For me, this is a relatively low-hanging fruit, because in my mind, I can think of many ways of replacing cobalt. This is much, much harder, because this is a big daddy material. It's very hard to replace tungsten carbide, right? So a lot of our work in the last 3 years has been focused on trying to minimize or eliminate use of cobalt, right? For example, we've been looking at what look like complicated chemistries, but they're not actually, right? We work on this with Höganäs, and they have for us made all these different kinds of formulations. The nice thing is, with all of these alternative binders, we get outstanding coatings, right? Same percentage of binder, but the binder chemistry is different. Some of it is completely cobalt free, right? These two, for example, we get excellent coating. So that was step one, right? We have investigated it to death almost. This little complicated slide, but if you look at summary, depending upon what kind of surface degradation you are talking about, yeah, so some of these are even better than the tungsten carbide cobalt chrome, which is the reference material. In some cases, they are almost as good. Are you guys playing tic-tac-toe? Then you can put it up on the screen. Yeah, let's all play for a while. Yeah, because I've been through that phase. It's good to play tic-tac-toe sometimes. It's nice. Yeah. But this is a summary. It's a great way to get rid of cobalt. Yeah, there are good ways to do that. What about tungsten carbide? Yeah, if I look at tungsten carbide on the Mohs scale or the hardness scale, I find there are many materials above tungsten carbide. Correct? All of these, for example. Why can't we spray those? Correct? Why are we stuck with tungsten carbide? Because all of these are conventionally very hard to spray. Yeah, they tend to degrade thermally much faster than tungsten carbide. Correct? So we've been looking at, for instance, titanium carbide as an alternative. It has all the good attributes that you would want in a wear-resistant coating. The challenge is, how do you retain TIC as TIC? You start with TIC, but after you spray, how do you get TIC in the coating, right? But we've been looking at different ways. Why is TIC exciting? Because it has no problems that tungsten has in terms of availability worldwide. Yeah, a lot of titanium available everywhere, including in India. India is a pretty large producer of titanium, actually, right? So we have looked at titanium carbide by a couple of prominent techniques here, and we always get a performance which is kind of halfway between the two popular materials that I showed for wear, tungsten carbide and chrome carbide. It's somewhere in between. Yeah, and there are a lot of results out there which consistently show the same outcome. Yeah, titanium carbide is very nice and gives you something in between those two. Yeah, a couple of years ago, actually during COVID, we started an interaction with Hyperion. It used to be part of Sandvik, but they have become separate now. And they are a company that makes grinding media actually, right? They don't make, they have nothing to do with thermal spray, right? So I gave a talk at Hyperion when everybody was sitting at home, including me. Their scientists were sitting at home. And one of my students is in charge, old master students. He's in charge at Hyperion. So one day he called me and said, everyone sitting at home, I want to expose them to new fields. Can you give a talk while you are sitting at home? I said, no problem, but I don't see any connect. He says, doesn't matter, let's do something. So I gave a talk to Hyperion. And I knew at the end someone will ask me, so what are the opportunities to collaborate, right? So I did some reading on their website. So as I expected, I was asked that question and I said, honestly, I don't see any way to collaborate because you work on grinding media, I work on thermal spray. I don't see much common ground there, but I am very surprised to see some of the grinding media you make. What is their grinding media? Their grinding media is diamond and cubic boron nitride, and they cap their diamond and cubic boron nitride with nickel by electrodeposition. Yeah, so very interesting way of making grinding media. Then they sell it as powder, or they somehow anchor it on grinding wheels. Yeah, but that's what they do. So I said, if you, I won't pay for it, but if you give it to me for free, I would love to spray these nickel-capped CBN and nickel-capped diamond. So that's how it started. We got some powder from them. This is nickel-capped diamond. We did some SCM. So each diamond particle then is coated with nickel phosphorus, right? It's cladded like that. And we sprayed that. Amazing, right? When you looked at microstructure, I wasn't sure if we would get a coating, but we did. Two things happened. One is we lost a lot of diamond, right? We could retain only 15% of the diamond. The second thing was all the diamond which was retained was much finer than what we started. So there was fragmentation of diamond, right? So those are still problems, but we found outstanding wear properties, right? We couldn't even see a wear track when we did wear test. It was that good, yeah? So we find this extremely promising. That has been the subject of a couple of our recent papers on thermally sprayed nickel capped diamond, very nice. And because of that, we also got encouraged to look at cubic boron nitride. We have kind of done the same. Again, pretty nice properties, right? 10 to the minus 8, 10 to the minus 7 specific wear rate. So this is also something we have published. But the next step for us is silicon carbide, because this is cheap. I don't mind losing 80% silicon carbide when I'm spraying. I don't want to lose 80% diamond or CBN, but silicon carbide I don't mind losing. So this is something we have started doing. Had them try and coat nickel phosphorus on SiC. They are not so successful, but the coatings are not bad, and so this is something that's in progress. So I think this is a good track for research, right? Finding new materials for wear, right? Which don't rely on scarce materials like cobalt and tungsten. How about liquid feedstock? I want to, so how much time do I have? 11 o'clock? Yeah? Okay. So I want to talk a little bit about liquid feedstock, right? How many of you have heard of liquid being used in thermal spray? Nobody, right? Yeah, that's why I'm talking about it. Let's talk about using liquid in thermal spray. What is the context? Why would you do a crazy thing like this, right? Let's go back to thermal spray and what we want to do. Yeah, you have seen this before. Our idea is to fully melt, to obtain dense coatings. Our idea also is to ensure that you get high velocity to achieve good adhesion. There is a problem here, but if you want high velocity, what does it mean? It means the particle residence time is very low, right? Once you inject and you want it to travel very fast, it has very low residence time. That residence time is of the order of milliseconds, yeah? So all action has to happen in millisecond time, correct? What does that do? It imposes an upper limit on your particle size, correct? So you need to pick your particle size such that in that millisecond time residence time, it will fully melt, correct? So this is easy to imagine, right? For that reason, your particles need to be below a certain size, right? If they are ceramic particles which are high melting, then they have to be finer. You have to be 45 microns or less. Otherwise, they don't melt in that short residence time that is available. If they are metallic particles which have slightly lower melting point, you can go a little bit higher. Maybe you will see particles which are 90 to 100 microns. But more than that, you can't spray. Yeah, I mean, you can't spray in the sense you will not fully melt, correct? So that imposes the upper particle size limit. Do you think there is a lower particle size limit for these spray powders? Is there a lower particle size limit? Yes? Someone said yes? Yeah. Why? Why is there a lower size limit? Coating will not be formed. Evaporate. Yeah. I mean, that's a remote possibility, but they could evaporate. Any other reason for why there is a lower particle size limit for feedstock? The main reason is that it doesn't flow. If your particle size is below a certain size, let's say 3 or 4 microns, it does not flow at all. It is like talcum powder. It sticks to each other, doesn't flow. It clogs in your powder feeder, it clogs in your tube that is carrying the powder. Somewhere it will clog, right? It doesn't flow. That's a big problem. Yeah, so the lower limit is governed by flowability. But if you had a wish list, would you like to spray a fine powder? You would, right? Because that is the way you get a refined microstructure. That's the reason why people get into nanomaterials and things like that, correct? So if I had a way, I would like to spray very fine powders, maybe submicron powder also, but for the longest time, we could not do it in thermal spray. So that is the motivation for liquid feedstock. Yeah, you want to overcome these feeding problems, correct? So two ways. One is put this fine powder, submicron or whatever, into a suspension. Put it in water, put it in alcohol, then suddenly it doesn't matter. Yeah, you can feed it like a liquid, correct? No problem. If you want to make life more miserable for yourself, you can forget this powder. You can use something called a solution precursor and hope that these particles will form during that millisecond time, and then those particles that are formed will serve as feedstock, right? So this is something very new that we have been trying. Let's talk about suspension a little bit. What happens if I use a liquid feedstock? These are the kind of pancakes or splats you will get. This is a slightly poor micrograph, but this has come from a single particle, from powder, right? About 100 microns. If you see this scale bar, about 100 microns. If I look at a pancake that comes from a solution, it's 1 to 2 microns, right? So I'm getting a splat size which is 2 orders of magnitude finer, and as a researcher that is very exciting, right? You're able to refine your building block now. You have small building blocks, so it has a lot more flexibility to accomplish whatever you want, right? Many people say, is this complicated, using liquid feedstock? In my opinion, not at all. Yeah, so this is conventional thermal spray. In this case, I am showing plasma. You have a powder feeder. Only thing you do is get rid of this powder feeder and have a liquid delivery device. Yeah, so it's simple. That's what I like about it the most, that it uses all conventional thermal spray hardware. Yeah, and therefore it's easy to adopt. Once people understand what benefits it can offer, it's easy to adopt by existing users. You just need a different feeder, that's all. Yeah, everything else is the same. I don't want to get into so much detail here. Yeah, but I did mention suspension and solution precursor. If you use a solution precursor, then you don't have the powder already in solution. Yeah, you need some reaction to happen, right, before a powder is formed. So this is even more complicated compared to using a suspension, right? And all of these, having a solvent or having all these additional steps happen, require additional thermal energy beyond what you need for melting, right? So if you look at literature today, you will mostly see these terms used: suspension plasma spray. You will not see suspension HVOF spray or something like that. I mean, you will see some literature, but not so much. Same with solution precursor. Solution precursor plasma spray, right? That is because plasma is ideally suited to provide the thermal energy that all these reactions need, right? On top of that, now you are able to feed this feedstock axially through the center, right? So people who were disappointed or unsuccessful with using liquid feedstock earlier, now suddenly can consider going back to liquid feedstock and get some very interesting results, right? And I will show you some of those. So while I was at ARCI, this was work by my first PhD student, right? We have already shown that even though this may be a very complicated looking process, if you do it right, you can actually form in flight these kind of particles, yeah, which can then become feedstock for coating, right? And with some careful process evaluation, we could show that if you don't do it right, you get all lousy stuff. If you do it right, you begin to get these kind of particles, which are few hundred nanometers, but certainly sub-micron, and that is ideal, correct? That is what you want to see, right? And similarly, if you do it right, you get junk on the substrate, but otherwise, if the stars are aligned and you have prayed hard enough, yeah, you get nice pancakes that can lead to formation of coating, right? So that was the beginning, and now we have used the same thing which we had learned from radial feeding and extended it to axial feeding now. So we are able to get very dense SPPS coatings, and so I want to make this point clear. If you use a suspension, all these additional steps are not necessary. If you use a solution precursor, you have these additional steps before powder is formed, and then rest of the process is the same, right? Is that clear? A little bit? Yeah. Why are some groups crazy about using suspensions? They're crazy because it was soon found that you could get columnar coatings like this if you used submicron particles in a suspension. Yeah, this is the main driver. Yeah, it's not exactly like a EBPVD columnar coating, but it's close. It gives the same effect. What is that effect? Yeah, it gives you the strain tolerance because it has this finger-like structure. So when you have heating and cooling, it can expand and contract and therefore accommodate stresses, correct? That is very crucial in a thermal barrier coating, which sees thermal cycling. You want this to happen, right? One more time, if it was dense, it would delaminate there in no time. Yeah, if it's columnar, it goes on forever. That's what you want, right? So now today we are able to get not just columns, but we are able to also design columns. We are able to get, we are able to decide what kind of column density we want. How many columns per millimeter? That also we can decide, right? So we've advanced a long way. We can play around even more, right? So we now know exactly what happens, right? If the particle goes like that, it doesn't form a column. If the particle goes like that, it forms a column, right? And the particle will go like that only when it is fine and doesn't have enough momentum. It goes with the gas flow, right? Close to the substrate. If it is larger and has enough momentum, it just goes straight and doesn't form columns, right? So we understand this very well now, and we know when columns form. We also know when columns don't form, right? And this kind of understanding for any process is crucial. Same with AM, and that's why I was emphasizing that you must look at evolution of microstructure. What happens at the beginning? What happens with little more time? What happens? I mean, does it stay columnar, or is it going from columnar to equiaxed in case of AM? In this case, how do columns grow, and in what circumstances do columns not go? Yeah. So this cartoon, without again getting into details, this uses ethanol as a solvent. If we use water or an ethanol water mixture, we don't get columns, and that's because when we are using this, the droplets are larger and then they go like that, and therefore not form columns. Yeah. When we use ethanol, because of the right kind of surface tension, etc., we get smaller droplets which travel like that and form columns, right? So if you're doing research, you need to get deeper and understand this. For us, this has been very useful for a couple of reasons. Because we know what is happening, we have been able to dispel many ghosts which existed about using liquid feedstock, because most people we spoke to say, liquid feedstock doesn't work. It doesn't give us good deposition. Yeah? Deposition efficiency is very poor. Yeah? But now all that has changed. right? We now, even 5 years ago, what used to take us 4 hours and use 12 liters of suspension, today we can do it in 12 minutes and use 1.5 liter of suspension. What does that do? It moves this from being exciting to an academic, because it will get nice papers, to becoming exciting on the shop floor, right? And that should always be our effort, that what we do in the lab should be exciting for the industry as a user, right? So suddenly we are in a domain now where all sorts of guys, including Pratt and Whitney, are after our small group in Sweden to help them get coatings like these, right? So that should be our effort at all times. The nice thing about us investing time in understanding how columns form was also the fact that we understood how to avoid forming columns, right? From the same understanding, now we know how to avoid forming columns. And that is important when you're looking at functions other than TBCs, right? Because we already said that do you want defects, do you want ports, depends, right? For TBCs it's nice, for wear it is not nice, right? So now we know how to avoid defects in SPS, and therefore even if we start in a lousy way, this was our very first trial with suspension chrome oxide. If you know, chrome oxide has many large applications, including in Anilox rolls. How many of you have heard of an Anilox roll? Anybody has heard of an Anilox roll? It's used in printing. Yeah, so typically it is chrome oxide coated and then laser engraved, right? So that's a typical method of making these Anilox rolls. So we started with chrome oxide, horrible coatings. If you see here, there is a tendency to form column. This is called a column head, yeah. But we don't want columns for chrome oxide, yeah. And because we understand the process much better now, we can go there very easily. This is suspension sprayed chrome oxide. So imagine columnar coating on one hand, imagine such a dense coating on the other, right? So we have great microstructure control, yeah, using liquid feedstock, yeah, and I think that has allowed us to do many more things. Right. Something else that is new is we have started using filaments or these flexi cords that we spoke about and trying to feed that into our axial plasma spray. We have learned many new things with that. It is very stable. It gives you a lot more choices. In a sense, it uses a polymer when you make this flexi cord, and that polymer in a loose sense works as a solvent, right? It is holding the powder particles together, and just like you want the solvent to evaporate immediately when you put it into a flame, you can have the polymer immediately evaporate, right? I think I'll stop here. It gets a little more complicated from this point on, but we have also been looking at, now we can spray with powder. That is, we have done that for donkey's years. We know how to use liquid. So can you use powder and liquid together? I mean, some of our recent projects have focused on using these together. And that is a pathway that we want to use now to combine, for example, a wear-resistant coating with a solid lubricant, right? So this is what we are looking at. This is a picture of both of them being fed together. Yeah, we are feeding powder through there and a liquid from the side, and works very well, right? And we have got some very nice microstructures. This is what we want: a large splat coming from the powder, a fine splat coming from the liquid, right? And this gives a good way for us to construct all sorts of composite coatings. One of the things that we've been very proud of is our ability to incorporate graphene. Yeah, many times when groups work with graphene, they go hunting for a graphene platelet in an SCM or TEM because there is not so much graphene that they can incorporate, right? But they want to show it in a paper, right? So you have to go find a graphene platelet. But that's not how it should be. You should get graphene everywhere, right? That's what we get now. Yeah, and for that reason we get amazing friction coefficient, right? by incorporating graphene in the coatings, right? But that's just an example. Uh, I'm going to fast forward because perhaps there is not so much time. Just wanted to show you we going into a boiler with our portable HVAF. Yeah, quite amazing to actually go there and see that happening. Uh, so this is so this part that you see here is inside this boiler. Yeah, this guy setting it up and then eventually spraying. So this has been a very successful. Do you see shock diamonds there? Yeah, did you see shock diamonds just now? Yeah, those are the shock diamonds because this gun is supersonic. Yeah, so many other applications we are looking at, SOFC, etc., etc. But yeah, I will end with this. Our recent project is on solid state thin film batteries. We started it just for fun to try and see if we can work with crazy materials like that. Nobody's ever sprayed them before because they are tough to spray. They tend to lose lithium. Lithium is very low melting, so your lithium tends to go off, right? So we started with this. Our ambition was very modest. Just wanted to see if we get any kind of coating at all. So we initially did that, got some coating. The next thing was to see if there is electrochemical activity. Yeah, we got some electrochemical activity which kind of didn't excite me so much because it's a long way to go to make it useful for a battery, but it excited some other groups who saw these results, and because of that we have got a much larger project now which allows us to not just look at LTO but solid electrolyte, the cathode as well. And then we spoke about greed. I am greedy, right? So now I was trying to see if we can build all these three together, right, to get a half cell or a full cell, and we are able to do that as well, right? But I will stop here. If you have any questions, I can take those, and if you have interest, mark this in your calendar, my anniversary date, yeah, and let's see if you are in Bhubaneswar for this short course that we are doing in tandem with the National Thermal Spray Conference. Yeah? Questions? Anything? Tired? Too much information overload? No questions? Nothing? Great. Do you have any announcements to make? There are no questions, looks like. Nope.
Then they need to write exams.
Yeah, I must give a quiz in the afternoon.
Yes.
Or tomorrow.
Tomorrow afternoon we'll have a quiz.
Shall we have a quiz tomorrow? People who fail don't get a certificate. Yeah. People who pass will get a certificate. You tell me, please. Try.
Okay.
For you, what is sustainability, first of all? Let's start there, and then we can see how it is relevant or how you can apply. It has or doesn't have that impact? What are you saying? If I am extending life of a component by 2 times, 3 times, 4 times, does it have a sustainability impact or it doesn't have? Yeah. If I am putting on a better thermal barrier coating which allows a gas turbine to operate at temperature which is even 5 degrees higher, does it have sustainability impact or it doesn't have sustainability impact? Repair, all that as well. So, what is laser coating? I want you to make some effort at least, right? Otherwise you can Google and you will find differences. But tell me, what is laser coating?
Of thermal, we can use instead of thermal, whatever energy we are providing through thermal here, why can't we provide through laser? What is the differentiation between thermal fading and laser coating?
You start, you give me half the answer, I will complete. What is laser coating? Let's start with that.
In terms of we are giving energy to the heat material through laser.
Yeah.
But here we are giving energy and heat input through some
Correct.
plasma.
So laser coating is, as an example, laser cladding, right? So we spoke about laser cladding yesterday. We spoke about thermal spray. We also spoke about the fact that both of these are oftentimes not competing but complementary, right? So yeah, laser cladding has a role to play. Can you get columnar coatings with laser cladding? You cannot get. Yeah. Can you get 5 mm thick layer by thermal spray? You cannot get. You can get it by laser cladding, right? So each of these has a role, right? And you need to think. I mean, this is something we spoke about yesterday. Now, I can't, we can't say now, oh, why can't we do all this by PVD? You cannot do, because it's a totally different technology, right? But what PVD does, nothing that I spoke about today can do what PVD does, correct? One more time, most important, these are non-competing technologies, all of them. Yeah. So these kind of questions after what we spoke yesterday should not at all appear. Correct? These are all complementary technologies. Each of them has a very specific role to play in a designer's portfolio, right? So please appreciate that. Any other questions? Or maybe you catch me quietly over tea if you don't want to ask it in open. Yeah? So,
Yeah, okay, we'll have tea break, 15 minutes, then we'll back to the next session of from the hexagon. Okay, Santosh Nagaraj is going to handle the next session. Okay, thank you. We'll verify. Yeah, welcome back to the second session of today's program. Here we are, our new speaker is from the industry from Hexagon, Santosh Nagaraju. Okay, just to brief about his profile, Santosh Nagaraj is a technical specialist at Hexagon, Indo-Pacific region and all. And Dr. Santosh Rajaraju leads the materials and manufacturing solution at Hexagon India. And he started his career from Scientific Farming Technology Corporation, US-based material farming simulation company, where he held various positions like technical support and business development. He also worked as in the SKF bearings in R&D team and all, and the farming and heat treatments and as well as rapid prototyping operations. And currently, Santosh Nagaraj is working in the with MSc Mark Software, technical specialist, and as well as BD for Indo-Pacific region. And he has done his master degree from machine design from RV College of Engineering, Bangalore. And Dr. Santosh has credit implementing the various advanced simulations solutions at global OEM and as well as 3D printing services in the R&D institutes, and he played a crucial role in the providing into the solution for the users in the conventional and as well as in the IT manufacturing process and all. You will deliver more on this the how we can drive the optimization for IT manufacturing, how we can use topology optimization, lattice structures, how we can minimize the weight of the materials, and also you will give the Simofact software how we can make use numerical modeling aspects in terms of IT manufacturing. Okay, with this brief introduction, I welcome you, Dr. Nagar. Please take this.
Okay, so hope I am audible for the people sitting in back. Okay. Good morning, and thank you for giving this opportunity to be part of GAN event. So I will start with my quick introduction. So sir has already introduced. So I have almost like a decade plus experience